So, hello, myself is Dibyananda Sahoo, and I'm going to present something on perturbation. So, my content is some brief ideas on perturbation. Then I will depict some maths with an example, then a question, then some maths again to explain the question, and some applications. So, brief idea. So, what is perturbation and why we need it? Basically, all the problems that we experience can be solved, almost all problems can be solved numerically, but sometimes we want to solve it analytically so that we can get a better grasp of the underlying mechanisms of the phenomena. So perturbation is a mathematical technique that helps solve difficult problems that cannot be solved exactly, but which are needed to be solved analytically. So it works on the principle that it breaks a very difficult problem into relatively simpler problems and handles a simple problem. After manipulations, we then retrieve the hard problem and get the answers analytically. So there are three steps of perturbative analysis. One is we convert the original solutions into a perturbative solution by introducing a small parameter epsilon. Then, assuming that the expression for the answer is in form of a perturbative series, we compute the coefficient of that series. Finally, we recover the answer to the original problem by summing the perturbative series, putting the value of epsilon appropriate. So these steps I will be explaining more as we go on. So here I present my example. So now let's look at this equation x to the power 5 plus x plus is equal to 1. So we want to solve this problem, but we know that this cannot be solved exactly. So we take the help of perturbative methods to solve this. So we have to insert epsilon somewhere so as to reduce the problem to a simpler one. But inserting epsilon is a tricky thing because if we insert epsilon somewhere else, we might not get what we want. And we also want that when we restore the value of epsilon, we should get the original hard problem. So first I start by inserting epsilon near x. So next steps are easy to follow. We assume that x is in a series of epsilon. We put it into the equation and simplify. Then we start collecting the coefficients for different powers of epsilon and equating it to the RHS. Here there is a necessary assumption that I've made. To do this step 4, we need to assume that our series, a Taylor series, to be unique. But a Taylor series to be unique, it has to converge. So as assumed all the way to convergence. After putting the values of x in that hard problem, we get a series in x that we see here. So this is the series that I finally get after putting the value of the the ansatz into the problem. So this series has a radius of convergence equal to 1.64931, and we observe that we can get the original hard problem by inserting the value of epsilon to be 1. So we are definitely safe here. We can put the value of epsilon to be 1 and get the answer. It will not diverge. So our answer is x is equal to 0.7544 to sixth order result, and the numerical value is around 0.75488. So this was simple. Next, we try to do something very different. One thing that the last point of that my perturbative analysis, that we recovered the answer to the original problem by summing the perturbative series to appropriate value of epsilon. We see that if the problem would have been x to the power 5 plus 2x is equal to 1, then epsilon is equal to 2 would have made the series to diverge. As we see here, the radius of convergence is only 1.6 something. So we need to deal differently in this case. Okay, moving on. So now I try to put epsilon in a different place. I put it near x to the power 5, and I repeat the steps 2, 3, and 4 as usual. finally I get a value for x in term of series. As we can see that this series has a radius of convergence 0.082, and we want epsilon to be 1 to recover the hard problem. So it's wasted. This series diverges fast and we cannot extract any answer. As we see, if we put the value of epsilon is equal to 1, then we get something around 21,476. So here one question rises. The question is, what just happened? We are just changing the placement of epsilon, and in one case we are getting an answer which matches very closely to the numerical results. But when I change the position of epsilon, I am getting a series that diverges and diverges fast, and we are getting nothing. So what has happened here? So the thing is, when we put the value of, when we put the epsilon near x, and when we tune the epsilon from 0 to 1, we see that the number of roots of the original equation remains same. We are getting, there was 5 roots for hard problem. For every value of epsilon, we still preserve the number of root, that is 5. But in the second case, when we put the value of epsilon near x to the power 5, we see that when epsilon becomes 0, we are losing 4 roots. So we have only 1 root with us, and other 2 roots are gone. And I specifically want to see where those 4 roots go and what has happened to them. So maths again. So to know where the 4 roots go, we can go to the second case and solve it in the limit epsilon tends to 0. So we need to solve this second problem in the limit epsilon tends to 0. So there we need to use a different method to know about the fate of those four. So one of the technique is method of dominant balance. It says that if my equation contains 3 terms and suppose one term becomes negligible, then the other 2 terms becomes asymptotic to one another. And I will be using that technique here to solve the problems. So I have 3 terms, epsilon x to the 5, x, and 1. So there are 3 possibilities to neglect one of those terms. One of the possibilities is in the limit epsilon tends to 0. I can throw away epsilon x to the power 5 such that my x becomes asymptotic to 1. The second case is when limit epsilon tends to 0, I can throw away x such that my equations become epsilon x to the power 5 is asymptotic to 1. And the third case, when epsilon tends to 0, I can throw away 1 so that epsilon x to the 5 becomes asymptotic to -1. So we get these 3 possibilities, but we don't know which one will be correct. So we need to check them. And as we know, mathematics it's itself a check on itself, so that we can get the wrong assumption through the method of contradiction. So we do the checking. For the first case, let's see in the opposite manner. Limit epsilon tends to 0. If x is nearly equal to 1, then we see that epsilon x to the power 5 should be very, very less than x, because epsilon has tends to 0. So the left hand side will be very, very less than 1. So our first assumption is correct. And here we realize something, that this is actually x nearly equal to 1 is actually the first root that we get from our answer, and that is actually 0.75, something around that. And this is this result. It is nearly equal to 1, we can say. I mean, it's 0.754 and it's nearly equal to 1. So not a bad not a bad approximation. So this first assumption was correct. And let's move on to the second assumption. In the limit epsilon tends to 0, if epsilon x to the 5 tends to 1, then x has to be very, very greater than 1. Because as we know, when epsilon is very, very low, I mean very, very near to 0, then x has to be very, very greater so as that the product becomes nearly equal to 1. But in the assumption, we assume that x is very, very less than 1. So here is the contradiction. So this assumption, the second one, is not correct. The final assumption. And here we will get what we are searching for. In the limit, epsilon tends to 0, epsilon x to the power 5 is nearly equal to minus x. If we simplify, we get x to be nearly equal to minus 1 by epsilon to the power 1/4. And here we see that when the value of epsilon tends to 0, the value of x tends to infinity. It's actually on the complex plane that the 4 roots go away towards infinity, and thus the magnitude of x is very, very greater than 1, which was our assumption. So we finally get to know where the other 4 roots leave when the epsilon tends to 0 in the second case. Okay, the applications to this perturbation theory is in quantum mechanics, of course, QFT, and mathematics, obviously. But here I want to focus on something. What we got in the second case is actually a diverging series. But and we also know that if we sum the divergent series, that is the most nonsensical thing to do, because we know the answer to be 0. But actually, mathematicians as well as physicists happy to see a diverging series. Almost every series that we deal in day-to-day life, I mean, not in high school, in actual experiments, will be diverging ones. But there is nothing to be sad over, because this diverging series can give very, very good results and in a very easy way. I can expand something on this perturbative analysis, because there are some important points that has to be discussed, but I thought I had less time, so I skipped on. If you okay, so I can say something on this perturbative analysis. The thing is that this method of perturbation, you need some foresight to choose a particular position of epsilon such that the problems become simple. Because when we why we're using perturbative technique, because we want to reduce a hard problem to a simpler one. By putting the value of epsilon to 0, we get a simple solution, and putting the appropriate value of epsilon, we recover the hard solution. Here we have to emphasis has to be placed in such a way that when epsilon tends to 0, the unperturbed problem that it is exact solve and cannot solve the hard problem, because in my when I'm placing epsilon near, you see that when my epsilon goes to 0, then my equation becomes x to the power 5 is equal to 1, and I know exactly what are the 5 roots of x's are. So you see this unperturbed problem is actually one of the boundary conditions I'm applying in this series x is equal to an into epsilon to the power n, such that I can get further coefficients of an. So here is one of the things that I skip. Also here in the second case, I mean in the recollection part, when we have x to the power 5 plus 2x is equal to 1. When we put epsilon is equal to 2, we see that the series diverge. But do we actually get into trouble here? We will see that we actually do not. This diverging series is worse when you sum it to get the value of x. But we can, and various mathematical techniques to extract information from this diverging series in very subtle way, and we can get very good results from this diverging series. So I haven't, I mean, this was not a part of my presentation, but there are techniques called Pardes summations and all, where even if epsilon becomes 2, we know that the series is that series will diverge, but still we can get the answer to the value of x. It's not a problem. Okay, okay, that's it. That's it. I have stopped. I mean, I have finally completed my slide. Thank you.